NASA's James Webb Space Telescope is an infrared space observatory that launched on December 25, 2021 from ESA's launch site at Kourou in French Guiana on board an Arianespace Ariane 5 rocket. The $10 billion telescope, which happens to be NASA's most powerful space science telescope ever, is tasked with probing the cosmos to uncover the history of the universe from the Big Bang to alien planet formation and beyond. After much anticipation, the telescope has finally detected its first signal among the stars. Let's talk about how this came to be and what the telescope found. According to NASA, the James Webb Space Telescope will focus on four main areas. It will look to study the first light in the universe, the assembly of galaxies in the early universe, the birth of stars and protoplanetary systems, and planets. Since its launch, the observatory has undergone a series of science and calibration tests, including sunshield deployment, telescope deployment, instrument turn-on, and telescope alignment. The James Webb Space Telescope is the product of an impressive international collaboration between NASA, the European Space Agency, and the Canadian Space Agency. According to NASA, the research for the JWST involved over 300 universities, organizations, and companies across 29 U.S. states and 14 countries. The nominal duration for the telescope is 5 years, but the goal is to stretch it to 10 years. The telescope is expected to study the early stages of the universe after the Big Bang started the universe as we know it today. In the first stages after the Big Bang, the universe was a sea of particles such as electrons, protons, and neutrons. This is why the light was not visible until the universe cooled enough for these particles to begin combining. Another thing the JWST will study is what happened after the first stars formed. This era is called the Epoch of Reionization because it refers to when neutral hydrogen was reionized by radiation from these first stars. Looking at galaxies is a useful way to see how matter is organized on gigantic scales, which in turn gives us hints as to how the universe evolved. The spiral and elliptical galaxies we see today evolved from different shapes over billions of years, and one of JWST's goals is to look back at the earliest galaxies and better understand that evolution. Scientists are also trying to figure out how we got the variety of galaxies that are visible today and the current ways that galaxies form and assemble. The last decade has seen vast numbers of exoplanets discovered, including with NASA's planet-seeking Kepler Space Telescope. JWST's powerful sensors will be able to peer at these planets in more depth, including imaging their atmospheres. Understanding the atmospheres and the formation conditions for planets could help scientists better predict if certain planets are habitable or not. NASA has discovered that the telescope finally captured its first grainy images of a distant star. The first images taken by the Space Observatory have identified starlight for the first time using its NIR-CAM instrument, which is also responsible for helping keep its primary mirror segments aligned. Webb's first image of the sky was taken in the very early morning of February 2, 2022. The image shows a star called HD 84406. The starlight was seen through each of Webb's 18 mirror segments in its primary mirror, so the resulting image shows a mosaic of 18 scattered bright dots. As Webb aligns and focuses over the next few months, these 18 dots will slowly become a single star. To make this image happen, the team had to factor in how misaligned the mirror segments, which are slowly and carefully aligning, were at the time, since not all the segments were facing the same direction. This requires the team to capture many images of this region of the sky to find the starlight with all 18 segments. Webb captured more than 1,500 images in total in this first observation. Additionally, this process required many Webb systems to act together as an observatory for the first time in flight. Even in this preliminary image, the initial results are very similar to the simulations performed by scientists before the telescope launched. This mission milestone is not taken lightly by the astronomical community. The Space Telescope faced decades of challenges and delays and, after launch, had to undergo a risky deployment with hundreds of single-point failures that could have doomed the mission. But now, safely unfolded and at its destination in space, this incredible early data from Webb has sparked cautious but overwhelming excitement from scientists around the globe. Webb will continue to align and focus its mirror segments so that they all act as one and can laser focus their view on distant cosmic objects. As exciting as these first few images may be, they are merely the start of an exciting journey for the telescope, which will see it explore everything from the start of the universe to studying distant planets. JWST will see the universe primarily in infrared light. Once its hulking golden eye opens, the observatory's exquisite sensitivity will allow the telescope to spy on the faint, faraway signatures of the first stars and galaxies that populated the universe. That sensitivity will also help it directly observe alien worlds, though nobody could have planned to use the telescope for this purpose when it was designed. When JWST was conceived in 1989, planets orbiting other stars had not yet been discovered. Planet formation theory suggested such worlds should exist, but the first exoplanets weren't announced until 1992. Recently, exoplanet hunters, such as NASA's Kepler Space Telescope, have revealed that worlds orbiting other stars in the Milky Way are as common as grains of sand on Earth. That abundance affords the JWST team a remarkable opportunity to study some of the most intriguing worlds in detail. By blocking the light of planets' parent stars with an instrument called a coronagraph, JWST can directly image some of these faint, faraway worlds in orbit, even those that might still be forming. The telescope can peer through alien atmospheres and determine what the gassy shrouds are made of and how they've evolved over a planet's lifetime. And it can read molecular signatures in the dayside glow of planets. After around 6 months into its mission, JWST will begin drinking in starlight and studying faraway worlds. As planets pass between their stars in the telescope, for a brief moment, their atmospheres will appear in silhouette, illuminated by the starlight shining through from behind. In that starlight, Webb will read the signatures of the gases the light passed through. A grab bag of extreme systems and planetary oddballs are among Webb's early transiting targets, including WD-1856b, a giant planet that orbits a stellar corpse, and HD-80606b, a planet whose orbit looks more like a comet's elongated, lopsided loop around its star than a planet's more circular path. Those extreme systems could contain clues about how different kinds of planets form and survive, and by surveying the gases clinging to a multitude of worlds, JWST will help scientists understand how a planet's size, temperature, and evolution are linked to its climate and other characteristics. Many of the telescope's early observations will target hot Jupiters, a class of planets we don't see in our solar system. Whipping around their stars in mere hours or days, these giant worlds are among the most common types of planets discovered so far by astronomers. The researchers will put all 4 of the telescope's instruments through their paces, and they will look for the ratio of carbon and oxygen in the planet's atmospheres, which contains information about where the planets formed. Another intriguing type of planet that we don't see in the solar system is the super-Earth, or the mini-Neptune. Worlds that are bigger than Earth and smaller than Neptune, like Gliese 486b, GJ 1132b, and K2 18b. Finding out whether these planets have atmospheres and what those atmospheres are made of is crucial for determining whether they might be habitable. Whether such worlds could be habitable hinges on where and how they formed and how they evolved. Some could be the stripped cores of former Neptunes, which dims the odds for habitability. Others sit right on the border between large rocky worlds and small gas worlds, a transition that scientists don't fully understand. Other early targets include hot rocky planets that are snuggled up to their stars, making them more like roasted lumps of charcoal than overheated puffballs. On these worlds, which include 55 Cancri E and K2 141b, clouds made of rock and minerals might rain lava, creating a landscape that defies imagination. JWST will also target each of the 7 rocky, roughly Earth-sized worlds in the TRAPPIST-1 system. These planets orbit a small nearby star about the size of Jupiter, and 3 of them are temperate. TRAPPIST-1e, among the early targets, offers perhaps the best chance of detecting Earth-like conditions, while TRAPPIST-1c, another early target, is closer to its star and probably Venus-like in temperature. While JWST will transform our understanding of the worlds that populate our galaxy, the telescope is unlikely to spot signs of life unless scientists are extremely lucky. That type of observation is just on the edge of the telescope's capabilities, and it would require an oversized chunk of observing time. Detecting distant alien biosignatures means looking for combinations of gases or chemical elements that scientists wouldn't expect geologic processes alone to produce. And while astrobiologists have some ideas about what we could look for, methane, ozone, and other metabolic byproducts, it's not clear what form alien life signatures might take. If you found this video informative, you may also like this one about the LUVOIR mission, which is scheduled to be the successor to the James Webb Space Telescope. Do you think the JWST will finally find signs of extraterrestrial life? Please share your thoughts in the comments section below.